equilibrium and the reaction quotient. So we have a system that is at equilibrium. We can use the equilibrium expression to solve for either concentrations, or if we have the concentrations, we can solve for the K value. So let's say we had this simple reaction, A forming B, and K was nice and handily 1. What we could do is we could say, okay, here's our equilibrium expression. We have products, concentration of the products raised to their coefficient, so in this case 1, over the reactants raised to its coefficient 1, and then we can plug in which variables we have to solve for one that we don't. So for example, if we knew the equilibrium concentration of A was 2 moles per liter, and again we know what K is, we can put those values into our reaction, and we can easily solve for what the concentration of B would be at equilibrium. So that's a straightforward at equilibrium using a equilibrium expression. When we have a system that's not at equilibrium, what we can do is we can use what's called the reaction quotient. And essentially what this is it's used similar to how K is used, but for systems that are not necessarily at equilibrium. So they may have more reactants than they would at equilibrium, but they may have more products than they would at equilibrium, and they will make their way towards equilibrium, but they may currently not yet be at equilibrium. So we're going to use this same setup as an equilibrium expression, but since we don't know for sure that it's at equilibrium, we're not going to set it equal to K. We're going to set it equal to Q instead, and then see where we need to go to get to equilibrium. So we'll use Q to determine which direction a reaction has to go to get to equilibrium. Again, does it have to shift to the right in order to produce more products to get to what they would be at their equilibrium concentrations, or does it have to shift to the left to produce more reactants to get to what they would be at equilibrium? And it's going to be set up the exact same way that we'd set up an equilibrium expression, reactants on the bottom, products on the top, with their coefficients as exponents. And again, because we don't know if this is at equilibrium, and probably it's not, we're going to be not writing K, we're going to be setting this equal to what's called the reaction quotient, or Q. So we can find out what Q is by plugging in the concentrations of those products over the reactants raised to their coefficients, and we can compare it to K, and it'll tell us which direction we would have to go to get to equilibrium. So let's say we plug the values in, we plug the concentration of the products raised to their coefficients, and we divide that by the concentration of the reactants raised to their coefficients, and we find out that our Q value is the exact same thing as the K for the reaction. That would tell us that we are at equilibrium, in fact. However, if we plug in the values and we say, okay, our Q value is actually larger than the known K for that equilibrium system, that's going to tell us that we need, or it will shift to the left in order to get to equilibrium. And if you think about what this means, is it's saying that there are essentially, your Q value is too big for what it currently is. It's going to have to shift to the left. It's going to have to consume some of those products, because again, we determine Q by putting the concentration of the products raised to their coefficients divided by the concentration of the reactants raised to their coefficients. So that number ends up being too big compared to what it should be when it's at equilibrium. That's essentially saying that we've got too many products. So to get rid of that, we're going to have to shift to the left. Conversely, if it turns out that our Q is smaller than our K, so we plug in the numbers and we say, okay, at this point in time, our Q value is smaller than what our known K value will be at equilibrium, we're going to have to shift to the right. And again, what that means is we don't have enough products. If Q is smaller than K, K is what they would be at equilibrium, Q is what they currently are. So if Q is smaller than K, what that means is there's not yet enough products. We need the numerator to be bigger. So we need to shift to the right and produce more products. And again, the numerator is the product. And so if we shift to the right, we will get more products, and our Q will get larger till at one point it'll be the same as K, and that's when we're back at equilibrium. All right, so with these ones, often these types of calculations, we have some of the concentrations of the reactants or products. Often we have the K value given for the known reaction, and what we're going to be doing is we're going to be solving for what the concentrations of the unknown, either reactants or products, are once it gets to equilibrium. So we're going to be using, again, the equilibrium expression. We're going to be using our known K value, what it should be at equilibrium, but we're going to have some values that we don't know, so we'll be using a variable to solve for those. So the steps to do this quickly would be to, first off, we need to know which direction the reaction is going to go. And that's where our Q is going to come in. Because again, we're probably not at equilibrium. So we're going to find out which direction we need to go to get to equilibrium. So we solve for what Q is, we compare it to our K value, and we say, do we need to shift to the right? Do we need to make more products to get to equilibrium? Or do we need to shift to the left, make more reactants to get to equilibrium? We're going to use an ICE table to keep track of our numbers, to keep things organized. And again, we're not going to have all the values in there, so we're going to use a variable for the ones that we don't know. We're then going to use our equilibrium expression, so equilibrium expression, because that tells us the relationship of the K value to the concentration of the reactants and products raised to their coefficients, so that we can find out for the concentrations that we don't know. And that may or may not be easy to do mathematically. We'll look at two examples. And once we have solved for this, we'll essentially have all the values that we need. All the numbers in our ICE table will be filled in, and we'll know what the actual concentrations are at equilibrium for the things that we did not know at the beginning of the question. So let's use this as our example. We've got two reactants, two products, nice 1, 1, 1, 1 as our coefficients. We've got our K value of 8.3. So if we started with 1 mole of each reactant, and it's in a 5-liter container. Remember, in our ICE tables, we're always going to be putting in the concentration of moles per liter. So 1 mole in 5 liters. We want to know what the concentrations at equilibrium are for each of the reactants and products. Notice that they are all gases here. So first off, let's look, based on where we are now, which way does the system have to go? Does it have to go to the right or to the left to get to equilibrium? And that's what Q tells us. And this is pretty simple for this question because we don't have any products. So it has to shift to the right. Whatever Q happens to be, it's definitely going to be less than 8.3 because we have 0 products. But we can test the math just in case you want to divide by 0 again. Divide 0 by something. If you have no products, your Q has to be 0, and therefore it has to be smaller than what your K is, which means we definitely have to shift to the right. So anytime you don't have products, you know Q is 0, you know you need to have shift to the right to make some products to get to equilibrium. Again, you probably don't need to actually calculate that. As long as you have no products, you know it's got to go right. Again, if the question did start with some amount of products, then you'd actually want to check it out and see which way you're going. All right, so for our ICE table, again, set up your table below the reaction itself. We'll look at the initial concentration, the change in concentrations, and then finally figure out what those equilibrium concentrations are. Now, obviously, the question's asking for these equilibrium concentrations, so right away we won't have these values, but we will use a variable, and then we'll solve for them. So given in a reaction, we have 1 mole in 5 liters, so we have 0.20 moles of carbon monoxide and water vapor, and we know that our reactants, it didn't say anything about them in the question, so as long as it doesn't say so, we have to assume that they are 0. We don't know any of the equilibrium concentrations. So if we knew that this was going to be like, I don't know, 0.1 or something like that, then it would be super easy. We could go and we could fill in our table and we'd be done. But we don't know those equilibrium concentrations. So what we're going to do is we're going to say, okay, the one thing I do know about the equilibrium concentrations is based on the equilibrium expression. I know what the K value is, and I know that the K value is the ratio of the concentration of the products raised to their coefficients, and that's over the concentration of the reactants raised to their coefficients. So I know something about the relationship between these concentrations here. So I'm going to use a variable to put that in and then solve for that variable and know what those equilibrium concentrations are. So first off, I know we're shifting right, so these start out at 0.2, and they're going to go down by some amount. I don't know what it is yet, but let's just put an X for that. These products are going to increase by the same amount because it's a 1 to 1 to 1 to 1 ratio. So whatever amount the reactants are going down by to get to equilibrium, we know the products are going to be going up by that amount. So then we can say that we're going to start with 0.2 and we're going to go down by X for both of the reactants, and then the products concentrations will just be 0 plus X, which will be whatever the X value is, will be their concentrations at equilibrium. So now we need to find out what this variable is. And again, since there's a mole ratio between the reactants, each of the reactants and the products, we know that this change is going to be following that mole ratio. So we really only have one variable to solve for. We just have to work it through the equation. Our equilibrium expression, again, the concentration of the products raised to their coefficients, which is 1 in this case, and 1, divided by the concentration of the reactants raised to their coefficients, which again is 1 and 1, and that's set equal to our K value. So now, let's get rid of that unneeded work there. Now essentially we've got an equation. We have one variable in it. We just need to solve for that variable. So the quickest way to do this, based on these numbers and based on the fact that all the coefficients are equal to each other, would be to simplify out and say, okay, well, this is really just x squared over 0.2 minus x bracket squared. And what that means is we can root both sides, and then we don't have to worry about solving with an x squared and an x. So we root both sides. That's going to give us both plus and negative 2.88 equals x over 0.2 minus x. Bring the 0.2 minus x over and solve for x. We're going to get two values there. And again, I encourage you to work this out on your own. See those two values here. We need to determine which one is not the real value, which one's inadmissible. And that's going to be based on the numbers that we start with. So we started with 0.2 moles of reactants. So if we're going down by x, you can't subtract more, you can't decrease by more than 0.2, right? You can't have antimatter reactants here. So this number here, 0.306, is inadmissible. It is too large to be one of the values for x, and so x is 0.148. Now we just need to come up with a concluding statement. State the concentration of the reactants. They start at 0.2, they went down by 0.148, and so both of our reactants will end up at 0.050. Our products have gone up by essentially 0.148, so we can round that up to the nearest sig dig at 0.15 moles per liter for each of the products. All right, so that's fairly straightforward because we were able to root both sides. Let's try a little bit harder one. So if we don't have a perfect square, imperfect square, we're going to have to work a little bit harder on the math. Same idea, same setup for the question. And what you'll see is with this one, again, we've got 2 moles of these, or sorry, 2 moles of hydrogen. We've got 3 moles of iodine here. They're going to go through a reaction, and we're going to end up with a product. We have our K value. So we're not going to be able to work out a perfect square with this one. We're not going to be able to root both sides. Let's set it up though. Again, we know based on the fact that we don't have any products, the concentration of the products has to be 0. Therefore, Q is 0. Therefore, Q is less than K. Therefore, it has to be a shift to the right. Set up your ice table. And again, a column for each of the species. Plug in the numbers that we have. We don't have any reactants, so we know that's going to be 0. We don't know any of the equilibrium concentrations, and we don't know any of the changes, so we're going to have to use a variable in our ice table here, and then use the equilibrium expression to solve for that variable. So again, we're going to say that the reactants are going down by some amount. It's a 1-to-1 ratio for them, and the product is going to be going up because these are 1 to 1 to 2, so the product is going to be going up by 2. And again, feel free to set your variable to anything you want, but if you set the lowest coefficient to x, then all other coefficients will be some multiple of x. Otherwise, you have fractions to worry about. So 2.00 minus x, and we have 3.00 minus x, and then our concentration of product will be whatever x is times 2. And again, I would get the smallest molar coefficient, so in this case the ones here, set them equal to x, and that makes this 2x, because if I decided to, I could say this guy's going to go down by x, and therefore these guys are, up by x, and therefore these guys are going to go down by half of x if I wanted to, but nobody likes fractions that much. All right, plug that into our equilibrium expression. And again, just let me write this out. We're getting this from our concentration of our products here. So this is our HI. And again, its coefficient is 2, so the exponent is 2 there. And then we have our concentration of our hydrogen with the exponent of 1, and our concentration of our iodine with the exponent of 1. So that's where we're getting these numbers. We're plugging in the equilibrium concentrations from our ice table. We're plugging in our K value given in the question, and now we have an equation with one variable. We can solve for that variable. Unfortunately, because our concentrations of products are not the same number, we don't have a perfect square. We can't root both sides. So we're going to have to expand out our brackets, and then we're going to have to do the quadratic. So work through it, but to set up for the quadratic, we're going to set our equation equal to 0. So expand out your brackets, put everything on one side, so the equation is equal to 0, and you should end up with 21 squared minus 125x plus 150. Make sure you can do that step. Then plug it into your quadratic. Either you or your calculator can work through it, but when you're done, you should end up with two values for x, one at about 4.3-ish and one at about 1.7-ish, and only one of them is real, one of them is inadmissible. We have to look at what they're saying in the ICE table. And again, because we're starting with, we have 2 and 3 moles per liter in our ICE table. If we were to subtract 4.3 from either one of those, we would end up with a negative concentration, and that is impossible. So therefore, x is equal to 1.667. Then it's just a matter of saying that as your answer. So if x is 1.667, what does that mean for the concentrations? Hydrogen started at 2 and went down by 1.667, so it's 0.333 moles per liter. Iodine ends up being 1.33, and then hydrogen will be 2 x's, so 3.33 moles per liter. All right, so realize that we had a quadratic there because our coefficients of our hydrogen plus our iodine formed our 2 hydrogen iodides. And so we ended up, because we had a coefficient of 2 here, that means in our equilibrium expression with our products of HI, it had a squared there. And then we also ended up with our reactants had, oh, no, that wasn't a square, that was a 1. And our iodine as well. They had coefficients of 1, but we multiplied them by each other. So we ended up with x squareds here. So we had to use a quadratic. But realize this coefficients of this ended up being x, right, squared. But realize this coefficient, what if this coefficient was like 3? Or maybe it's a reaction with 4. Or maybe you had more reactants and their coefficients were 3s and let's say, I don't know, a 5 even. Realize what that would do to your exponents in your equilibrium expression, and realize what that would do when you went to do the math with it. So let's say, for example, you had this reaction. Here's a reaction, and let's say we want to deal with it as an equilibrium system and find out what its concentrations were. If you looked at the coefficients to get this equation to balance, they're ridiculous. So you can imagine trying to solve for x when it's got a exponent of 16 on there, let alone all the other exponents. So essentially the math becomes too difficult to be worthwhile doing. So we have a shortcut in chemistry to avoid dealing with such math whenever we can. Not always can we, but when we can, we avoid it. So let's refer to this as skipping the quadratic, or worse. I don't know what you'd call it when it's to the 16, but it would be terrible. So what we do is we say, okay, well, how good are these numbers anyways, right? If k is really, really small, remember k represents how much product you have at equilibrium. So if the k is really small, so what that means is the shift to the right from the reactants to the products is pretty small. That means that the x value that we're solving for in these equations is going to be also very, very small. And if it's small enough compared to what we're taking it away from, we could probably just ignore it. So let's look at what that will look like. And if we can ignore it, we've got a lot fewer variables to solve for. We use what's called the 100 rule, and depending on how accurate you want to be, this could be 100 or a larger number, maybe 500. But essentially what it does is it looks at the k value, which again is representative of the shift that you're going to need to do to get to equilibrium, versus how much of the reactant, in this case, if we're moving to the right anyways, it would be the reactant that you're comparing it to. How much is it going to be subtracting from this reactant? Because remember, we're starting with a reactant and we're shifting, in this case, as written, to the right. Let's say it'd be different if you're shifting to the left, but let's say you're starting with the reactant and you're shifting to the right. The k value essentially says how far you're going to shift to the right. And if that is really, really small, this calculation would work out with a very large, because remember the reactant is quite some number, and k is really, really small. When you took whatever the reactant's concentration was and you divided by k, you get a really big number, something probably much bigger than 100. And what that's saying is that the shift to the right is going to be quite small, and it might be small enough, assuming it's this calculation works out to be a bit larger than 100, it might be small enough that we can ignore our x value. So we're going to call this the 100 rule, and we're going to use it as a way of deciding if we can ignore our x value within the ice table and within our equilibrium expression. If so, again, we can simplify out x, and so maybe it was x to the 16 or something like that. If we can ignore it, it doesn't matter if it's really small as 16 or it can essentially be ignored. Let's see how that looks. Before we move on, realize we're not saying x itself is actually 0. We're just saying it's pretty small compared to something else. And so often we're looking at the reactant, we're subtracting it from the concentration of the reactant, or we're adding it maybe to the concentration of the product. That's where it's going. So what we're saying is x small enough to make a difference to that concentration value? That's essentially what we're trying to say. Let's look at some numbers and decide. We can validate this later and say, okay, we've made this assumption. Was it too big of an assumption to make, or is it okay? So to do that, let's look at these numbers here. So we have a certain amount of nitrogen, a certain amount of oxygen. They're reacting, producing nitrogen monoxide. And we have a K value. And this is sort of, you get a heads up as to, could you probably do it? This is a really small K value. So it's saying that the concentration of the products at equilibrium are going to be pretty small. So that means the change, the subtraction from the reactants as they move to the right to make the products, is going to be pretty small. And if it's small enough, there's going to be some places in our math that we can essentially say, okay, it's really small, let's just ignore it. Again, let's quickly check. Yeah, there's no product, so Q is 0. Now K is small, but it's not less than 0, so there's still going to be a shift to the right. So we have a shift to the right, even though it's not a whole lot. Check the 100 rule with this one. Anytime you have a small k, we can check the 100 rule and see what it works out to be. So again, take probably the limiting reactants concentration, whichever one there's that is the least of in terms of making the product, the one that would produce the least amount of product. Take its concentration and divide it by the k of the equation, and in this case 0.038 divided by 4.2 times 10 to the negative 8 is going to give you a giant number, which is definitely larger than 100. So what that's saying is that the shift to the right is pretty small. We could probably, we can and we will ignore x. Let's see where. So here's a reaction. Let's plug in the values we had like before. Again, we're going to be going down by x, though because k is small, we know x is going to be quite small. The oxygen is going down the same amount, 1-to-1 ratio. The nitrogen monoxide is going up by 2 times that amount. So here's where we can look at the 100 rule, how the 100 rule works. So what we're saying is that K is small. This shift to the right is going to happen, but it's not going to happen by much. So if we have 0.085 moles per liter of nitrogen, that doesn't seem like a lot, but remember X is going to work out to be very small because we know K is quite small, so the shift to the right is going to be like tiny shift to the right. And so the question is this X value, when we solve for it, is it actually going to make a difference to this 0.085? Because if it's really, really small, like 0.0000 something or other, it is not going to cause much of a difference. So let's say we had 0.085 and we find out what X is. And let's say, I don't know what it is, but let's say it's like something super small like that. You can do that math and find out exactly what that is. But when you go to factor in your precision, you look at your sig digs and say, okay, I got to answer in 3 sig digs, it's going to equal 0.085. So essentially what we're saying is this number, if it's small enough, this X, this change, if it is small enough, it will not affect the concentration of the reactants in this case, because we're shifting right, it'll not affect the concentration of the reactants enough to change how we deal with the number based on our precision anyways, right? So our numbers are always going to be rounded off a little bit. They're always going to be inaccurate to some amount. So if the change that we're going to do to them is so small that it's going to get ignored, it's going to be rounded off anyways, let's just not do the math. So making this assumption based on that test, the 100 rule, to say X is small enough, we can essentially pretend it's not going to be subtracted. It won't make a significant difference to the concentration of the reactants. Therefore, let's just ignore it, and it makes our calculation even easier. Now this one's not all that hard. We could do the quadratic. It's not that hard. This is more of an example. They can get to the point where you're going past the quadratic. You have to deal with cubes and whatever comes after cubes, and so you would really want to ignore in those cases. Now realize we're not saying x is 0. That's the difference. We're saying it's close enough to 0 when being subtracted from a larger value or added to a larger value. So we still want to know what x is, but we're just going to look at these cases here and say, okay, it's going to be small. It's not going to affect their concentrations very much, so we can just ignore it relative to a larger number. Okay, so it's like you find 20 bucks. Like 20 bucks isn't $0, right? But if Jeff Bezos finds 20 bucks, he's probably not too concerned about it, right? Because his net worth is so big that if it changes by $20, it's not a big deal. Kind of like what we're doing here. If we have these concentrations and they change by x, it's as if the x itself is close enough to 0 that we can ignore it relative to a larger value. We still want to know what it is though. So using our equilibrium concentrations right here, again, x can be ignored when being compared to a larger value, but when it's not being compared to a larger value, subtracted or added from a larger value, we're going to leave it in. Set up your equilibrium expression and plug in those values. A lot easier now because again, we don't have these minus x's in here, which we would if we couldn't ignore them, and therefore we don't have to deal with the quadratic in this case. We can very quickly solve for x. Obviously, x as a negative is going to be inadmissible, so our x value is 5.82 times 10 to the negative 6, which is pretty small. So we can validate this, and again, you probably don't need to do this formally, but let's walk through the steps for it. Is this that small? So essentially, often our measurements are going to be off by maybe a percentage or up to 5% anyways, and so there's no point in doing a lot of math that is going to be more precise than our measurements are anyways. So let's say we're setting this 5% threshold, and again, you can determine how precise you want to be and then do the math accordingly. But let's say we set it at 5%. What we assumed was that the concentration minus the x value is essentially the same thing as the concentration minus 0. So let's actually test that. We found out what x is, and let's see if you did subtract that from the concentration value. Is it about the same thing as not doing it at all? Is it about the same thing as if x were 0 relative to the concentration of the reactant? So let's look at the numbers. So obviously, when we ignore x, we're just treating the concentration of the reactant as if it were 0.038. If we did actually subtract our x value from it, we'd get 0.037999418. So the question is, when we ignore it or when we don't ignore it, is there a big difference? So essentially, how big of a difference is there between those two numbers? We can express that as a percentage. Look at the difference between them. This is just a percent difference calculation. And there's a 0.02% difference between whether we ignore x or whether we use x. There's a 0.02% difference, and our measurements are going to be way more off than that. So definitely we can ignore x in this case. It is small enough to not change the concentration of the reactant significantly, therefore it can be ignored. So we have our x values, we have our concentrations at equilibrium based on those x values, and again, you would say that the concentration of the reactants essentially did not change, and our concentration of our product is 2 times 5.82 times 10 to the negative 6. Which is 1.2 times 10 to the negative 5 moles per liter.